All right. Can you all hear me? Excellent. Good. Thank you for having me. I am always happy to talk about robots, and particularly if it comes to how we can give robots more skills and make them a bit more intelligent. And that's basically the main part of what I'm trying to get to eventually in this presentation. So here you see the title is Manipulation Locomotion Using Soft Robots. You see here a human and a fish locomoting together underwater. That was a deployment where we took the soft robotic fish to Fiji. And that's always probably the most inspiring thing if you get somewhere to this point of taking your robot and actually going to a really exotic place to try it out. So if you have not had the chance to do this in your research, you're definitely in the wrong field. Okay, so with this being said, that's what motivates my work. So I'm driven by natural insights that inspire us in our research. One of my favorite examples is this fish that's swimming up the stream. You see this, some of you might have seen in a previous presentation, but if you have not, here, this is a very interesting phenomenon where you take a fish, you put it into a flow field, and it's going against the flow fields. And as you see, it's able to use the energetic vortices that are being sheared off on the top and on the bottom to swim upwards. The only small caveat here is that this fish is actually dead. So it's not doing this in any conscious manner whatsoever, and it's not using any muscles. So consider this. I find this amazing because being able to see that nature can even do such intricate things is by itself interesting and something that we should aspire towards to replicate or to produce. Another thing that I find also particularly mesmerizing is an octopus that can swim underwater, uses several tentacles. All of them have many muscles, and it can do all kinds of things that we would dream of a robot to do. So it can morph around a cage, it can go into this cage, it can capture this grab, it can go around it and touch and sense and feel and do this all in a very short lifetime. And then if you go on land, we can look, for example, another very continuous system is the elephant trunk. It has the ability to smell, to feel, to touch, to grasp. And with this, you can see it has about 40,000 muscles just alone in the trunk. And additionally, all the sensing capabilities of feeling and smelling, and while having a very poor vision. And the elephant really needs it to survive. So we have all these flexible, adaptive, efficient systems in nature. How can we reproduce this in robots to be also dexterous and safe is the key question, I would say. So transforming basically now existing mechanisms that people have published on and taking them to make capable soft machines is driving my research. So we would have things like an underwater mechanism, or we would have crawlers, or we would have single arms or grippers. They all have shown some sort of a mechanism, but they haven't really shown any intelligence or any ability to work as a really integrated system. Very little systems have shown that so far. And if they've shown it in very limited environments. So what is really the goal of our research and of the community overall is to answer a couple of questions. How well can we achieve biomimicry? How well can we explore new spaces? And how well can we manipulate spaces? And from this, we go towards the eventual goal of doing underwater locomotion that can be similar to nature. So we can use it to spy on marine life, or we can do more flexible, more adaptive manipulation that can be used in various settings you can imagine, or even do such intricate things like an octopus that is capable of you trapping that octopus into a jar. It's never been trapped into a jar before, and it's capable of escaping from the jar by just figuring out what policy it needs to apply underneath that lid to get out of the jar. All right, so the major research areas are, so I'm looking into the materials and the making of soft robots, into how to model and optimize these robots, and I will talk about this a bit more later. And then how do you make integrated systems with this? And how do you control and apply machine learning techniques to these systems to actually give them some more capabilities? So we have fish robots, we have grippers, we have arms, we have these everting robots, and we have these arms and grippers. And today I will only talk about some things related to the fish robot and things related to this arm and gripper system that you see below. Okay, so back to Fiji. totally worth it. You should build a robot and find a good excuse to go to an exotic place. Here we built a robot. What was unique about it was the fact that we could combine a soft tail with an integrated system, actually shown in working underwater. So you had a camera on board. We have a couple of other sensing modalities. So it's an interesting platform to now do more with it, to give it more autonomy, to give it the ability to actually freely roam the ocean and freely learn about the space. And so you might be wondering, so what's so special about this fish? Well, let me explain the soft robotic aspect of this. So a soft robotic actuator is basically a system where you take a cavity of some sort. You can design that according to your problem. You combine it with something non-extensible that's shown here in blue. And then you start inflating this whole thing. And by inflating it, it will start bubbling up. It will start deforming into a way that you want it to deform until it can, for example, get very overblown, but still do this bending motion that you might want to have for your particular system. So now in this whole process, you have achieved the design step of coming up with a fishtail, and then you have to come up with a casting procedure of how to make that actual fishtail in reality, or you could also use printing or other methods. I will not talk about this today. And then you have to figure out what is the source of pressurization. May it be hydraulic, pneumatic, or something completely different. Also things that interest me. I won't talk about them today. And finally, you have to test them in the real environment. And so this is what a soft robot basically is. Now you put this into a soft robotic fish. Then you basically have the tail in the back, which is shown here in green. And you can split the whole system in further parts that just make the whole thing work. And that's really always the biggest challenge in the end. So to show that we can actually not just have an interesting mechanism, but we want to deploy that mechanism in the real world. So you need something like a buoyancy controller so you can control the depth. You need dive planes to be able to dynamically go up and down, similar to how a shark does it. And you need also control electronics and other aspects like a camera on there so you can actually observe the marine life. And on the other side, you need a module to talk to this thing. Eventually, you want to get rid of that module. You want this robot to be capable to do everything by themselves. But in the meantime, you have to build them. You have to come up with acoustic signal protocols that can actually talk to your robot underwater over longer distances. Okay, so here is a time snap of how this, the time-lapsed sort of like series of going over the cabbage patch, which is this particular reef, one of the reefs that we tested it on. And what we were able to do with this, we primarily collected a lot of videos and camera images with the fish eye lens in front of the fish, and we're able to show that we actually get other interactions with this fish compared to a thruster-based system. So there was a step towards, can we use biomimicry by having something that wiggles and undulates in a way that a real fish would undulate and wiggle. So now you wonder, what is the AI behind this? Well, as I already mentioned, there is one direction of giving this particular fish more autonomy by using its onboard and possibly also offboard computing capabilities. Another thing that also interests me, and I will talk about this now, is how could you quickly optimize the design and the control of the system so that you actually can come up with a new design that is swing faster, that's more efficient, maybe more biomimicry, and any of those things or all of those things combined. So you would come up, let's say you have this full design space of various swimmers, and it was actually really a thing that I was struggling with when I first was catting up this whole fish. It's like, what inspiration should I take to build this fish? Should it be a Nemo? Should it be a submarine? What should it be? I mean, there was even this idea in the room in the beginning when I started doing this is, can I take my soft actuator, buy an off-the-shelf sort of submarine system, cut it partially half, take the thruster off, put my tail on it, and start trying it out. I gave it up very quickly because it would have looked completely non-inspiring, but it would have been probably much faster to just do this. Anyhow, so how do you do this? And from a computational perspective, this is how I'm going to address this first. So there's multiple modeling approaches for soft robots. You can use something called a reduced order FEM, or like just take an FEM and find a reduced order model to it. There you could just start off with a minimal parameter model to begin with, and that model already captures most of the continuous deformations of your structures. Or you could use something called differential projective dynamics, which is another take on finite elements. But the nice thing about this particular implementation we're using is that it's differentiable, and I will tell you in a second why that's interesting. Or you could even go completely away from FEM models and use something that we are calling a deep stochastic Kopman operator. So you're going towards more of a black box system. So now I will speak about this differential projective dynamics. So we published a work we call DiffAqua, which is basically a differentiable computational design pipeline that allows us to take robots and use shape interpolation to find an optimal shape that is not any of the ones necessarily that we start off with, but it could be anywhere in between of this design space, while also co-optimizing for the control policy that we're using to actuate this robot. So you start off with an unoptimized design, and you end up with an optimized design. And what does that mean? So you see in the center, you have a certain control signal that you randomly initialize, you have a certain design, and then on the right side, you come out with a new shape of the fish and with a new way of actuating the muscles in the fish. So let's say you take 3 different designs to start off with, just as an example. And you place muscles into each of these designs, but the way you place the muscles and the way you can interpolate them, the muscles will scale automatically. So then you get this continuous interpolation space between all of those different designs. That's your parameter space that you can now optimize for. That's what we see on the left side. So we have these different geometric designs. We then take a controller design. Ideally, we just start with a neural network. The neural network nicely is also differentiable. That's a nice feature of it. It can capture far more complexity than just a simple sinusoidal controller could, for example, capture. And then we run this forward in our simulation. So granted, in this particular simulation, we are simulating the solid mechanics, and we're making some assumptions about the fluid interactions. And those are very simplifying assumptions due to the complexity of that problem by itself. And then in the end, we come up with a final loss based on some optimization criteria. That, for example, could be our objective is we want to swim forward very quickly. And so then we propagate back the gradients from that found in a single value of our loss. We propagate that back, and we keep running this as an optimization problem using gradient descent. So what do we get here as a result is on the top, you see these 3 different swimmers that I was just showing you. And those are not optimized in the design. The only thing we optimized there was the control signal. And the bottom, as a result, we have this hybrid swimmer that's a bastard between all of those 3 different designs. And here you also see we had adjustments to the muscles, and also here you see visualized how the actual individual muscles are being, through this neural network, being controlled, telling it how you should be firing the different individual muscle cells to swim forward. So you can do this for various shapes. So we start off with an initial guess of a hybrid. You see it on the top. And in the end, we come out with this shark shape design, which is something that you might intuitively think if you would have seen the biggest shape, this was like 9 different designs that we're taking here. This makes sense. And you can do this for multiple objectives. So you're not stuck to just one objective. You could do multiple objectives here at the same time. So it could be high speed, it could be medium speed, or even high efficiency. You can really go the whole Pareto front with this approach and cover more than just one objective at a time. So here you see it's the high-speed swimmer that gets much further than the high-efficiency swimmer, which uses less energy, but therefore can swim so fast. So now this is all so far in simulation, and we now have been recently thinking about how can we bring this into reality. So we have been something we're calling sim to real, developing a way of learning the material parameters and the hydrodynamics using this differentiable simulation approach. So we can compare our real experiments that we're doing in a test setup where we can measure forces, and we can also simulate part of the hydrodynamics, like physically, actually experimentally run them through, and then also capture the formation behavior of the tails. And we then trying to figure out what are the material parameters of the spine, of the soft actuator, the things that are essentially making up this tail. So we can actually capture nonlinear effects such as the buckling here, and we can also learn what are the actual thrust forces that for prediction, which will help us in the future step to do a better job in predicting what thrust forces should the whole network be experiencing and predicting in the simulation. So what we can, so just to give you an idea, so here we basically start off with having different fish shapes. So we use different numbers of chambers, use different hardnesses of materials, and we also use different actuation frequencies. And all of these we're feeding into our optimization pipeline, and then in the end we can figure out, basically, I'm trying to show this here in a simplified way, we can figure out what is the actual Young's moduli for the body, for the spine, what is the actual Poisson ratio for both of these materials. So we're getting a higher dimensional parameter space. We're trying to figure out what are the actual parameters for each of them just by observing the experiments that we're doing. And we're comparing this to a gradient-free approach, and we can do this significantly faster with this differentiable simulated approach. So one open question that I would be curious to see what you're thinking about this, and also looking here at the time, we're almost at the end, is can we actually learn the multi-physics in an unsupervised manner? Is one of the major questions that I'm currently wondering about and also interested to work with people on. Because if we can do a better job in understanding the multi-physical effects of a solid mechanical problem where we have a continuously deformable fish and also understand the fluid flow behaviors, we would do a much better job in optimizing the whole structure altogether. So what can we do to have a differentiable approach to this and do this very quickly is one of the really guiding questions for us. So in the interest of time, I caught myself speaking a bit too long. I want to just acknowledge my team at the SRL, at the Soft Robotics Lab. And with this, I want to go to the overview slide and say thank you for your attention.